Okay, and here's the video when I'm doing questions 31 to 40 then in this paper. So we've got in the electrolysis of aqueous potassium nitrate KNO3 using inert electrodes, so that'll be graphite or platinum. 0.1 moles of a gas was formed at the cathode, the negative electrode. Now panic is correct this time because of course this is an electrolytic cell, so the cathode is the negative electrode. So which is correct? You got the gaseous product at the anode, okay, so that's at the other electrode, the positive one, and how much gas is going to be formed at the anode. So what's the gas being formed at the cathode? Well, if it's KNO3 aqueous, then of course we're not going to get potassium ions go to the negative electrode, we're going to get hydrogen ions, which will gain a couple of electrons to form hydrogen gas. So that's what we get at the negative electrode. So it's not hydrogen, because that's the wrong electrode. What else have we got present? Well, the nitrate, we don't have to worry about the nitrate, because what we've also got, because we're in aqueous solution, is hydroxide ions. And then you get 4 hydroxide ions. You just need to remember the equation gives you an oxygen molecule plus 2 molecules of water with a release of 4 electrons. So it's going to be one of these two, that's correct. We're going to get oxygen produced at this electrode. Now it's a case of how much. Well, if we compare these two equations, let's sort of put the hydrogen one alongside it. So notice that we need 2 electrons in the hydrogen equation, but 4 in this one. So if we double up everything in the hydrogen one, so 4 hydrogen ions plus 4 electrons gives us 2 molecules of hydrogen. Well, we can see, right, okay, there's a 2-to-1 ratio. So if we get 0.1 moles of hydrogen being produced, with that same current, we'd get half the number of moles, because now we've got the same number of electrons, we get half the number of moles of oxygen, so that'd be 0.05. So we're looking for B to be the right answer. Yeah, don't forget, you could combine these two half equations then, and then the electrons would cancel out. So basically you'd have your 4OH minus, and then plus your 4H plus, gives you oxygen, plus water, 2 waters, plus 2 hydrogens. Again, you could get it that way. Okay. And then looks like we're into the organic section part. So what are the functional groups in the aspirin molecule? So what we've got here is a benzene ring, remember, and here we've got the carboxylic acid, and here we've got an ester functional group. So we've got the CH3, C double bond O, O, and then to a carbon. So what have we got? Well, we don't have an ether, because remember an ether is just a COC, so no ether. A carboxyl, well, yeah, we've got the carboxylic acid, so that's fine. And we've got the ester group here, so that's fine. So it's 2 and 3 only. Which molecule has a tertiary nitrogen? Well, remember, a tertiary nitrogen's got 3 carbons attached to the nitrogen. This one's only got 2, so this one is secondary, so it's not that one. This one is actually a quaternary nitrogen because it's got 4 carbons attached to it, so this one is kind of like 4 degree, so it's not that one. This one, we've got 1, 2, 3 carbons attached to it, so that's tertiary, that's looking correct. Let's try this one. This one's only attached to 1 carbon, it's got 2 hydrogens on it, so this one's actually a primary one. So we want this one here, which again, what that would look like, it would be 2, 1, 2, 3, and then the nitrogen, and then the methyl. And of course, if we wanted to name that, that would be N dimethyl propanamine. Not that we need to name it, but C is the right answer. What can be determined about a molecule from the number of signals in its NMR spectrum? The bonds present, well no, they're talking about infrared for that. Molecular formula, no, you're not going to get the molecular formula from that. The molecular formula we could probably get from a combination of mass spectrometry and combustion analysis. The molecular mass, well no, we're going to get that from mass spec. That's the useful bit. Number of hydrogen environments, yes, that's what we want, because that's where your proton is, basically, the number of hydrogen environments. So you just need to know that one. And then 35, what is the major product of the reaction between 2-methylbutene and hydrogen bromide? Well, let's draw this molecule out first of all then. So 1, 2, 3, it doesn't matter if I draw cis or trans because we're going to react the double bond anyway. Here I've gone trans. So that's 1, 2, 3, 4, and we've got a methyl group on position 2 as well. So then when this reacts with hydrogen bromide, the first thing it's going to do is grab a H plus from the hydrogen bromide. and then kick that out. So we're going to form a carbocation, and we're going to want to see which is the most stable carbocation. So where can I attach this hydrogen? Well, we could have the hydrogen attached here, and then the carbocation is there. So that would give us this species where we put the hydrogen here. Alternatively, we could have it where the hydrogen goes on this carbon and we put the carbocation here. So there's our hydrogen, and then of course the bromide would come in and react with the carbocation. Let's put some lone pair. So which one's the most stable carbocation? Well, it's this one, because more alkyl groups, this one's got 1, 2, 3 carbons attached to it, and they can donate electron density towards it and stabilize it. So the more substituted carbocation is more stable, and therefore this is going to be the major product. Okay, so this would be the major one, and then that would give us the bromine on there and this bit off. So labeling that through, if that's position 1, 2, 3 and 4, basically we're looking for 2-bromo, 2-methyl butane. So which one's that? That would be D. Okay, so we're looking for D there. What is the product of the reduction of 2-methyl butanal? So butanal 1, 2, 3, 4, aldehyde at the end. Position 1, 2, so there's where the methyl group is. Now when we reduce that with something like sodium borohydride or lithium aluminium hydride, it's going to reduce to an alcohol, which will then be a primary alcohol. 1, 2, still got the methyl group on there. So what would this be? Well, the alcohol group's on position 1, we still got the methyl group on position 2, so it's going to be A. Okay. Ketone, well, you're not going to get a ketone, sort of certainly not reduction, and that one would be the product of oxidation. So if we'd oxidized it, then we would have got D. So that's what we're looking for. 1, 2, 3, 4. Which molecule is chiral? Well, again, you can help yourself if you draw these out. So butane, 1, 2, 3, 4 carbons. Chlorine on that carbon. What else is attached to it? A hydrogen. Well, that's looking pretty good actually, because I've got a methyl group, an ethyl group, a hydrogen and chlorine. So 4 different groups attached to that, so I'm quite liking that. 2,2-dichloropentane, 1, 2, 3, 4, 5. The chlorines are both on position 2. So yeah, no chiral centers on that one, because here we've got the 2 chlorines are obviously the same group. Everywhere else has got at least 2 hydrogens on it. Propan-2-amine, 1, 2, and then the amino group is on position 2. So we've got 1, 2, 3 carbons, amino group on position 2. So whilst there is a hydrogen there, we've got 2 CH3 groups, so it's not this one. And then 4-hydroxybutanoic acid, 1, 2, 3, 4. Carboxylic acid in there. If that's position 1, 2, 3, and 4. OH group out here, well, that's still got 2 hydrogens on there. 2 hydrogens, so no chiral centers on this one. If it had been 3-hydroxy or 2-hydroxy, then yes, we'd have chiral compounds, but it's not. So it's A, where we've got the 4 different groups attached to this carbon. The molar mass of a gas determined experimentally is 32 grams per mole. Its literature molar mass is 40 grams per mole. Okay, so what we've got to think on this one? Well, first of all, let's work out the error. So remember, the error is the difference between the two values. So it's basically 32 minus 40, or 40 minus 32, not too worried. So that's 8, so that's the error. And then the percentage error, remember, is the error divided by the true value times 100. So if the error, the difference is 8, divided by the true value, and the true value is the literature value, which is 40, times 100. So it's 8 divided by 40, well, that is basically 1 over 5. So that's a fifth, times 100, or it's equivalent to 100 divided by 5, which is 20. Okay? So you've got your 20%. So you can even get that from sort of the fact that once you've worked out the error, and then 8 over 40 is a fifth. Well, what's a fifth as a percentage? Is 20%. Or if you just then multiply by 100, 100 divided by 5 is 20. Not too tricky with the maths. And then on to the last two. So first of all, what is the density in grams per centimetre cube? Well, the units give you a clue as to what you need to do. You can see it's grams divided by volume. So basically there's the mass divided by the volume. So our density equals 34.79 divided by 12.5. Now you don't have your calculator, but you can see it's like, okay, it's not far off 3 it's going to be, because sort of 34 divided by 12, well, 3 12s are 36, so it's obviously not going to be these two. Those would have been if we'd done the sum the wrong way round, I'm guessing, 12.5 divided by 34.79. Now, I don't know which of those would be more. I can't get one of those two values, my sort of the maths wouldn't be good enough, but that's not what we're looking for here. What we're looking for here is just the appropriate number of significant figures. So we know it's one of these two. Now there's 4 significant figures here, but the volume only has 3 significant figures. So our answer, we're only entitled to put to the same number of significant figures as the least precise data. So because that's 12.5, we can only put an answer to 3 significant figures the same as this. So it has to be this one. If it had said 12.50, then we'd have gone with this one, because there would have been 4 significant figures. And then the last one then, technique to measure bond lengths and bond angles of a molecule. You've just got to remember that's X-ray crystallography, and that's all you really need to know about it. Okay, remember this is to use to work out what bonds might be present, like a C double bond O. This tells you the molecular ion peak and the mass of any fragments of a molecule. And this tells you the different hydrogen environments within a molecule. Okay, so it's X-ray crystallography, which you can also use to tell you which enantiomer you have. If you have an isolated enantiomer from a pair of optical isomers, X-ray crystallography will tell you which chiral center you actually have. Okay, hope that was useful then, folks.